Hello friends, I welcome you in lecture number 10 on relations. In this lecture we are going to discuss one more relation related to its properties. We are going to discuss whether given relation is satisfying given properties. Here relation R is defined on this set of integers, and definition of relation R is we have to consider ordered pairs of those integers a b such that first integer a is equal to second integer plus 1, that is order pair ab such that a equal to b plus 1. For example, if we consider say b equal to 3, then a is 3 plus 1, that is 4. Similarly, suppose b is 0, then a equal to 0 plus 1, that is 1 0. So this is the nature of elements in our relation. First element is equal to second element plus 1. We can have negative elements also. Suppose b is minus 2, then a equal to minus 2 plus 1, that is minus 1. And we have to check whether this relation is having all these properties. We start with the first property, which is reflexive property, and we know that relation is reflexive if every element is related to itself, that is order pair a comma a belongs to R for every a in the set of integers. Now this is possible if a equal to a plus 1, and this implies 0 equal to 1, that is a contradiction. Therefore this is not possible that a belongs to R for every integer a. Therefore this relation is not reflexive. So if certain property is not satisfied, we have to give particular order pair or particular element in a given set which does not satisfy given property. For example, if we consider 5 in the set of integers, then we can say that 5 is not equal to 5 plus 1. This means 5 comma 5 is not in the given relation. Definition of given relation is we have to consider order pair AB such that a equal to b plus 1. So 5 belongs to R if phi equal to 5 plus 1, but that is not possible. Therefore this relation R is not reflexive because 5 is not related to itself by this relation. Relation is reflexive if every element is related to itself with the definition of that relation. Therefore it turns out that given relation is not reflexive. Now we have to check for symmetry property. So for symmetry property, whenever AB belongs to R, we must have BA belongs to R. Now AB belongs to R if A equal to B plus 1, and BA belongs to R if B equal to A plus 1. That is A equal to B plus 1 implies B equal to A plus 1. This is also not obvious, or it is obvious that this is not true. So we have to think for particular element. We have to find out particular values of A and B such that AB belongs to R but BA is not in R. So we consider that we can take this order pair. Suppose I consider B equal to say 0, then A will be 1. We consider B equal to 0 and A equal to 1, that is A equal to B plus 1, 0 plus 1. So for 1 comma 0 belongs to Z, 1 0 belongs to R. What is the reason? Because first element equal to second element plus 1. 1 0 belongs to R because 1, that is first component, is equal to second component which is 0 plus 1. but we can say that this 0 1 is not in given relation. Why? Because here first element and second element plus 1, these two are different. This is equal to 2. So here that property is not satisfied. First element equal to second element plus 1. Therefore 0 1 is not in R. So we have obtained two elements 0 and 1 in the given set of integers such that 1 0 belongs to R but 0 1 is not in R. This implies that R is not symmetric. If R is symmetric, then whenever AB belongs to R, we must have BA belongs to R. But that is not true here. For 1 0 belongs to R, we are not having 0 1 belongs to R after reversing the order of components. Therefore, this relation is not symmetric. Now we check for next property. What is next property here? It is transitive property. So for transitive property, we have to check that whenever AB belongs to R and BC belongs to R, we must have AC belongs to R. So first we try to prove this and see whether we are able to prove it or not. If there is some difficulty in the proof of that property, then that gives us the idea that property cannot be true. So we should try by taking particular elements. But suppose first we try by taking arbitrary pairs. Suppose this happens, or where we have this possibility that AB belongs to R and BC belongs to R, then this implies A equal to B plus 1 and this implies B equal to C plus 1. Now we want to prove that AC belongs to R. That is, we have to check whether A equal to C plus 1 or not. So for that I can substitute value of B in this equation and we can see B is C plus 1. So here I will obtain C plus 2. So that is not equal to C plus 1. So therefore we are not able to prove this property. That gives us the idea that property may not be satisfied. So we have to try by considering particular elements. So suppose I consider this element. Here I consider 0, then I have 1, that is 1 equal to 0 plus 1. So 1 0 belongs to R. Okay, recall that definition of relation is AB belongs to R if A equal to B plus 1. Here B is 0 and 0 plus 1 is 1. Therefore this is in the relation R. Now we have to consider another pair in such a way that first component of that pair is 0. So here what element I have to write? So we can see from this that B equal to A minus 1. So 0, here A is 0, so 0 minus 1 is minus 1. So here if I add 1 to this component, I will obtain 0. So we have obtained that 1 0 belongs to R and 0 minus 1 belongs to R. And we have to check whether 1 minus 1 belongs to R or not. Now 1 minus 1 belongs to R if 1 equal to second component plus 1, that is 0. So here we have 1 equal to 0, which is not possible. So here we can see 1 0 belongs to R, 0 minus 1 belongs to R, but 1 minus 1 is not in R. Therefore this relation is not transitive. We have obtained two ordered pairs such that AB belongs to R and BC belongs to R, but AC is not in R. So we can write here that clearly 1 0 belongs to R. Why? Because 1 equal to 0 plus 1. Similarly 0 minus 1 belongs to R. Why? Because 0 equal to minus 1 plus 1, but 1 comma minus 1 is not in R because 1 is not equal to minus 1 plus 1, that is equal to 0. So this property is not satisfied, that first component equal to second component plus 1. Therefore R is not transitive on this set of integers. Now next property is antisymmetry. We have to check whether given relation is antisymmetric or not. So we just recall the definition of antisymmetry. Definition says that whenever AB belongs to R and BA belongs to R, then we must have A equal to B. In other words, if A and B are distinct elements, then these both are not possible. If A and B are different, then either AB belongs to R or BA belongs to R. Now for the proof, here we can see that AB belongs to R if A equal to B plus 1 and BA belongs to R if B equal to A plus 1. So whenever this is possible, we have to prove that A equal to B. But from this we can see that A equal to B plus 1 and B equal to A plus 1 is not possible at the same time. So therefore this is not possible. Either this possible or this possible. AB belongs to R and BA belongs to R is not possible here, because AB belongs to R if A equal to B plus 1, BA belongs to R if B equal to A plus 1. So this is not possible at the same time. Either A equal to B plus 1 or B equal to A plus 1. So therefore this relation is antisymmetric. We can prove that this is not possible at the same time. Suppose we assume that this is possible. Suppose AB belongs to R and BA belongs to R. Suppose this is possible. Now we are assuming that this is possible. Now if this assumption is wrong, then we will have contradiction at some step during the further procedure. Now if AB belongs to R, then we must have A equal to B plus 1, and if BA belongs to R, then we must have B equal to A plus 1. From this I can write that A minus B equal to 1, and from this I can write that A minus B equal to negative 1. Now here left hand side are same, therefore we have 1 equal to minus 1, but this is not possible. So this is a contradiction to the assumption. What is our assumption? Our assumption is that AB belongs to R and BA belongs to R. But if we assume this, then we obtain 1 equal to minus 1, which is not possible. That is, we are getting a contradiction. And this contradiction we are getting because our assumption is wrong. Therefore, AB belongs to R and BA belongs to R is not possible. Or we can say that either AB belongs to R or BA belongs to R. For AB belongs to Z, we have to specify that A and B are integers. This implies that our relation is antisymmetric relation. So in this way we can decide whether given relation is satisfying certain properties or not. And this is all about this session. I hope you like it.